Welcome to the week one lecture. This week we will be covering a little bit from chapter 1 and then covering chapter 19 on vibrations and waves.
The topics that we'll cover from chapter 1 include what science is, what physics is and why it's considered the basic science, and then we'll go over the steps of the scientific method. Let's just start here with what science is, since physics is a science course. It's good to understand that word science and what that means. So science is a body of knowledge. It's an ongoing human activity, which means it's something we are always doing, and it has beginnings that precede recorded history. And science is essentially, it's a way of looking at things and trying to systematically or step by step obtain information about the things that we are studying. Physics is considered the basic science, and I'll get into here why. Your textbook says that. So science is broken into physical science, which is the study of non-living things, and life science, which is the study of living things. Physical sciences include things like geology, astronomy, chemistry, physics, and life sciences include things like biology, zoology, and botany. Physics underlines all of the sciences, so it includes things that you study, such as motion, force, energy, matter, heat, sound, light. Chemistry looks at how all those things are put together, how different types of matter are put together and how they work together. So it's putting some of the concepts of physics together and understanding how they interact. Biology is looking at how chemical compounds work in living things. So it's even a little bit more complicated and using a little bit more science, you could say. So physics includes the basic ideas that underlie all other sciences. And so for this reason, it is considered a basic science. Let's continue with physics as a basic science. And a lot of people think that physics is very hard. And the reason that they tend to think that is that physics uses a lot of math, or it can use a lot of math to explain all the different things that it's looking at, to explain why things move at a certain rate and how things interact. So because of the math, a lot of people get intimidated. This course, however, is called conceptual physics, which means that our understanding of physical concepts is going to come from understanding big ideas on how things work rather than on focusing the math behind those ideas. We will still do some basic math, but we won't do as much or as complicated of math as you might in a more math-based physics course. In spite of the math that comes along, you're probably pretty familiar with many of the most common physics concepts and have a general understanding of what each of these things are. Things like gravity, light, heat, you really tend to understand those things, know all about them. Whereas a lot of other sciences, you're learning tons of new words and trying to memorize those words and just what the word relates to and then what it is. Such as when you start biology, you're learning all the cell parts and you have to learn the cell names and then what those parts do. And so in physics, at least most of the words that you'll study, you have heard before. And I hope that that will make the course easier for you. Section 1.1 in your text deals with scientific measurements and how physics uses basic scientific measurements to learn about what's going on in the world. So measurements are a hallmark of good science. Having something to measure means that you can quantify it, put it into numbers, and know something specific about it. And your text has a quote from Lord Kelvin, who was a physicist in the 1800s, and he came up with the Kelvin temperature scale, which is what the Celsius scale is based off of. And his quote is, "I often say that when you can measure something and express it in numbers, you know something about it. When you cannot measure it, when you cannot express it in numbers, your knowledge is of meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever it may be." And he was really a big proponent of the metric system and of measurements in general. So in physics, measurements will be an important part of physics because it's knowledge about things that can help us understand what we are studying. Continuing on with scientific measurements, we grew up in the US using standard inches and feet, and most of the rest of the world uses the metric system. And the reason for this is that the metric system, once you get familiar with it, is really much simpler. It's based on units of 10, and the prefix, or the word before the word meter, tells us how many meters are in a unit. So really you just need to know some basic Latin, that milli means 1/1000th, centa means 1/100th, and kilo means 1,000th. And there's some other basic terms, but those are a few examples. So for example, millimeter means milli is 1/1000th, so it means 1/1000th of a meter, or that there are 1,000 millimeters in a meter. Centimeter is 1/100th of a meter, or there are 100 centimeters in a meter. And example of going larger than a meter, kilometer, or kilo means 1,000, so kilometer means 1,000 meters. In the US system, you'd have to memorize that there are 12 inches in a foot, 5,280 feet in a mile. So there's all these numbers that you're trying to memorize, whereas kilometer, you know, kilo's 1,000, so kilometer's 1,000 meters. It's simple numbers to remember, and it's also very easy math when you're dealing with units of 10. And that helps out a lot when you're doing math problems in physics. If you're putting your units into the metric system, you're dealing with units of 10 and hopefully making the math much easier. There is no one scientific method. So here at KCC, we tend to use the same steps of the scientific method for all their labs, so that when you go from one science course to another, you don't have to learn new scientific methods in every course. But every textbook that you get, and if you were to look on the internet or anywhere else, you would see different steps. But in general, the main idea of the scientific method is that it's a set of steps that you take in the pursuit of knowledge, or to try to learn about something. And it involves recognizing that there's a problem, trying to collect data through either observing or doing experiments, and then formulating a conclusion about your experiments. So for this lab course, as I said, we will use the steps that KCC uses in all its lab courses, and those are on the next slide here. And the first step of the scientific method is to make an observation and identify a question. So for example, your flashlight doesn't light up, and you think to yourself, what might be wrong? The next thing is to propose a hypothesis, and a hypothesis is just a possible answer to your question. Doesn't mean it's the right or wrong answer, it's just what you think the answer might be before you do your experiment. So you might decide that the flashlight doesn't work because the batteries are dead. The next step of the scientific method is to perform an experiment and test your hypothesis. So you might come up with the experiment, if I replace the batteries, then the flashlight should work. The next step is your results, or collecting data from your experiment. And after you replace the batteries, does the flashlight turn on? So you would either have the data that yes, it turned on, or no, it did not turn on. And finally, you'll come up with a conclusion where you interpret your results. If the light does work now, then your hypothesis was correct, that it was the batteries. If your flashlight does not light up, then you need to formulate a new hypothesis. Perhaps the bulb is faulty, and then develop a new test for that hypothesis. And the very last step is that you would report for peer review. So you would let other scientists know about your idea, let lots of other people test your idea, and see if they come up with the same results that you did. So in science, you never want to just do an experiment once, because you could have just a fluke that you got the results that you did. And if you repeat your experiment multiple times and other people repeat your experiment multiple times, then you're more likely that you're getting the right answer and finding out the correct results. Overall, science needs to have an attitude or ideas of inquiry, experimentation, and willingness to admit error. So if you never try to inquire and learn new things, science would never progress. And we want science to progress and want to continue to learn new things about the world around us. Experimentation is the way that we learn about the world around us. So we need to experiment to find out if our ideas are correct or not. And then, very importantly, at the end, we have to be willing to admit error. So even if it's a very well accepted idea, if results start showing that that idea is not correct, then we might have to say that whatever idea we had needs to be reevaluated and come up with a new and better idea. Scientists, it says, are experts at changing their minds, and this probably isn't true in most of the rest of the world where you'd say you're an expert if you can change your mind. But in science, you need to be, like I said, willing to accept that if the results don't show are not consistent with what you thought was going on, then you need to be willing to come up with a new idea. And you have to accept whatever your experimental findings are, whether it's what you thought they were going to be or not. You need to accept those findings in science. So you're trying to be unbiased and not use your own opinions in science, but look at what the results show, and also look at antagonists, or people who have ideas opposing yours, to see why they have those ideas and if there's any validity in their ideas. Let's cover some basic terms here that often get confused. A fact is a close agreement by competent observers who make a series of observations about the same phenomenon. So, as the little cartoon says here on the right, facts are revisable data about the world. And we probably don't think of that when we think of a fact. We would think of it as being true and not revisable or not changeable. But we may have something we consider a fact, but if evidence ever showed that that was not true anymore, we would need to revise our ideas. So it's something that people think is true, but it's definitely not set in stone. A hypothesis is an educated guess that is only presumed to be factual until supported by experiment. And what this means is that it's what we think is the right answer, but really we need to do an experiment to determine if it really is the best answer for what's going on or not. A theory is a hypothesis or idea that has been repeatedly tested and verified over a long period of time. And a theory tries to interpret different facts that we have. And the reason why we say that a theory has been verified and not proven is we don't use the phrase proven, because someone could always disprove it later. So verified means the results show that it's likely that that's the right answer. But in science, like I said, we have to be willing to go back and admit error or reevaluate things if new data comes along at some point that doesn't support our ideas. A law or principle is a law is basically a hypothesis that's been tested repeatedly and has never been contradicted. For example, the law of gravity, we've shown in multiple experiments that things tend to be drawn into a large object. So for example, if the large object is the Earth, then there's a magnetic pull of objects towards the center of the Earth, and that's what makes things fall from the sky to the ground, what holds us on the ground so we don't float away. Whereas a theory is a synthesis of a large body of information that encompasses a well-tested and verified hypothesis about certain aspects of the natural world. Some examples of theories are, like in physics, the quark theory of the atomic nucleus. In chemistry, the theory of metallic bonding in metals, so that metals will bond together. And in biology, the cell theory, or the idea that all living things have cells. And theories are not fixed ideas. They do undergo change over time. Let's go through a few questions next. And ask which of these is a scientific hypothesis: that the moon is made of green cheese, that atomic nuclei are the smallest particles in nature, a magnet will pick up a copper penny, or that cosmic rays cannot penetrate the thickness of your conceptual physics textbook. as a hint, remember that a hypothesis is something that can be disproven. So that there is a test to disprove it. Think about that for a second. Move on to the answer. And all of these are scientific hypotheses. All of them have tests for proving wrongness, so they can pass a test of being a scientific hypothesis. Next up, we have which of these is not a scientific hypothesis. That protons carry an electric charge, that undetectable particles are some of nature's secrets, that charged particles bend when in a magnetic field, or all of them are scientific hypotheses. And the answer, undetectable particles are some of nature's secrets. So choices A and C can be disproven by experiments. Choice B has no test for wrongness, so you can't prove it wrong that it's nature's secret, so it is not a hypothesis. Next up, which of these often changes over time with further study? Facts, theories, both of the above, or neither of the above? Both of the above. Both of these can change. As we learn new information, we refine our ideas, and this is the same in science. So facts might change, and theories might change. A person who says that's only a theory likely doesn't know that a scientific theory is a guess, number of facts, hypothesis of sorts, or vast synthesis of well-tested hypotheses and facts. So next we're going to move on to chapter 19, which is on vibrations and waves. The answer is vast synthesis of well-tested hypotheses and facts. The word theory in everyday speech is different than its use in science. People often in everyday speech will say that's only a theory, meaning really that they would be referring to like that it's only a guess, whereas in science it's pretty much the opposite. It's that we have a ton of information to support the idea. So a theory means that we've got a lot of information on it and a lot of information saying that that idea is correct. The chapter 19 you're reading in this lecture will cover vibrations of a pendulum, a description of what a wave is, and how we determine wave speed, some different types of waves such as transverse waves, longitudinal waves, standing waves, shock waves, and we'll also go over wave interference. We will be skipping the section on bow waves, so if you want to skip that in your reading, you can skip that section there. A vibration is a periodic wiggle in time. So if you think of anything that's bouncing up and down, wiggling back and forth, that's a vibration. So a periodic wiggle in both space and time is a wave. So it has to move over space and it has to occur over some amount of time. A wave extends from one place to another. So for examples of waves are light and sound. And light is when you have an electromagnetic wave that doesn't need a medium to travel through. So it could just travel through open space and you would see the light. Sound is a mechanical wave, so it's something actually moving and it needs a medium or something to move through in order to hear that sound. So as we mentioned, a vibration is a wiggle in time and a wave is a wiggle in space and time. So a pendulum, you've probably all seen this. If you were to take a rod and have a string hanging from that and have a ball or stone at the bottom of that, you would have a simple pendulum. And a pendulum swings back and forth at a rate that depends on the length of the pendulum. So it doesn't depend on the mass of the weight at the bottom of that pendulum. So you could have a big ball or stone at the bottom or a small one, and it will still go back and forth at the exact same rate. And the reason for this, if you did not take Physics 101, is that all objects are pulled down by gravity at the same rate or the same speed and acceleration. So regardless of the size of that ball hanging at the bottom of the pendulum, whether it's heavy or light, big or small, it's going to be pulled down by gravity at the same rate. The time of one to and fro swing is called a period. So the time that it takes for if you think of the ball hanging, or even if you remember being a kid going on a swing, the time to start at one point, go to the other side, and come back to where you started is called the period. And the longer the length of this pendulum is, the longer it will take for the longer that period will be, or the longer time it will take to go back and forth, the longer essentially the swing that it's on. Let's do a review question. Throughout the lectures, we'll have some information and then some review questions that hopefully will help you understand the material and help you with your homework. So a review question here, a 1 meter long pendulum has a bob with a mass of 1 kilogram. Suppose that the bob is now being replaced with a different bob of a mass of 2 kilograms. How will the period of the pendulum change? And our answer, the period will remain the same. So the period of the pendulum depends only on the length of the pendulum, if you remember, not on the mass at all. So changing the mass won't change the period of the pendulum, or how long, again, it takes to go back and forth. Another question, a 1 meter long pendulum has a bob with a mass of 1 kilogram. Suppose the bob is now tied to a different string so that the length of the pendulum is now 2 meters. How long do you think the period of that pendulum will change? Or how do you think the period of the pendulum will change? And the answer is it will increase. So the period of the pendulum increases with increasing length of the pendulum. Now a wave is similar if you think of that period, the vibration going back and forth, or the pendulum going back and forth. A wave is essentially a back and forth motion. It's represented by a sine curve. If you have ever taken any geometry and gone over what a sine curve is. And if you don't know, it just looks like this up and down motion in this picture here. And a sine curve is obtained when you trace out the path of a vibrating pendulum over time. So if you were to put some sand in the pendulum and let it swing, the sand were to drop through a hole in the pendulum on a sheet of paper, as long as the pendulum swings back and forth, if you were to pull the paper slowly underneath that sand, you would end up with this shape here. And so the sand essentially would make the sine curve on the paper. When a bob vibrates up and down, a marking pen traces out a sine curve on the paper that moves horizontally at a constant speed. So essentially, you could do the same thing with a bob bobbing up and down or vibrating up and down. It would also make the sine curve if you were to trace out that motion of it going up and down, and you were pulling that paper out underneath it. It would have a constant speed and show you that up and down motion. Now, if you're looking at up and down motion of a wavelength, whether it's light or sound or a bob bobbing up and down, the highest point that we look at on that sine curve is the height that it goes up is called the amplitude of the wave. So if you were to look at a midway point, the distance between the top of the curve and that midway point is the amplitude. The distance from the top of one point to when it reaches the top of another point, and think of it as like a period, you've gone completely up and down, or down and up in this case. That distance there is called the wavelength. And the distance can be from any point on the wave, so you could measure the wavelength from the bottom of one point to the bottom of another point. You could measure it from, you could measure it from the midway point here to the midway point over here. And that is that distance there. If you were to measure that, that's the wavelength. Now, vibrations and waves have certain characteristics, and one is they all have crests, which, as we talked about, that's that high point on the wave here. That's known as the crest, and the low point on the wave is called the trough. So this kind of looks like a trough. This kind of looks like a crest. Crest is the high point, trough is the low point. Now, we already went over the amplitude and wavelength, but again here, the amplitude is the distance from the midpoint to the crest, or the midpoint to the trough, and the wavelength is the distance from the top of one crest to the top of the next crest, or the distance between identical parts of the wave. How frequently a vibration occurs is called the frequency. The unit of frequency is measured in something called hertz, or capital H, lowercase z, after Heinrich Hertz. And a frequency of 1 hertz is a vibration that occurs once each second. So if you were thinking of like that bob bobbing up and down, if it started at the top, went to the bottom, and went up again to the top, and that took 1 second, that would be a vibration of 1 hertz. If you were looking at your wave, it would be the time that you take to go through one wavelength, so the time that you take to go from crest to crest. Mechanical objects like pendulums have frequencies of a few hertz. Sound has a frequency of a few hundred or thousand hertz. Radio waves have a frequency of a few million hertz. Cell phones operate at a few billion hertz. Frequency refers to, it specifies the number of to and fro vibrations in a given time. So it's the number of waves passing any point each second. An example, if you had 2 vibrations occurring in 1 second, is a frequency of 2 vibrations per second. So again, the period is the time to complete 1 vibration, and in mathematical terms, the period is equal to 1 over the frequency, or vice versa, the frequency is equal to 1 over the period. So for example, if a pendulum were to make 2 vibrations in 1 second, the frequency would be 2 hertz, the number of vibrations per second. The period, or the time that it takes to do that, each vibration is half a second. So if your frequency was 2, you'd have 2 equals 1 over the period would be half a second. So a sound wave, let's do a review question. A sound wave has a frequency of 500 hertz. What is the period of vibration of the air molecules due to the sound wave? So is the period 1 second, 0.01 seconds, 0.002 seconds, or 0.005 seconds? And again, you're going to be using those formulas from the last slide. So we're going to use the formula period equals 1 over the frequency. So 1 over 500 hertz is our frequency, would be 0.002 seconds. Another question here, if the frequency of a particular wave is 20 hertz, what is its period? Is it 1 over 20, 1/20th of a second, 20 seconds, more than 20 seconds, or none of the above? The answer is 1/20th of a second. So if frequency equals 20 hertz, then time is equal to 1 over the frequency, which would be 1 over 20 hertz, which is 1/20th of a second. So the bigger the hertz, the more waves that you have going per second, or the higher the frequency is. Next, let's look at wave motion. So waves transport energy and not matter. So they're not moving. Matter is just all the stuff around you. And waves aren't moving matter, they're moving energy. So an example is if you drop a stone into a quiet pond and the resulting ripples don't carry water across the pond, they just move the water in that up and down or wave-like motion. Waves traveling across grass on a windy day are not actually moving grass. They're just, any distance. The grass might blow back and forth, but it's not actually going anywhere. But the energy of that wind is moving through the grass. Another example would be molecules in air propagate a disturbance through the air. So if there was some kind of disturbance in the air, the molecules in the air could move that energy through the air from one place to another. Now, wave speed describes how fast a disturbance moves through a medium. It's related to frequency and wavelength of a wave. So wave speed is equal to the frequency of the wave times the wavelength. So the longer your wave, the longer it's going to take to get from one place to another. But the quicker the frequency, or the more frequently the wave happens, the faster also your wave speed will be. An example is a wave with a wavelength of 1 meter and a frequency of 1 hertz. Essentially, you're just doing 1 times 1, has a speed of 1 meter per second. And wave speed we will typically measure in meters per second. So let's do another problem here together. If a wave has a wavelength of 10 meters and the time between the crests is 0.5 seconds and it's traveling in water, what is the wave speed? So to get wave speed, you're going to need the frequency times the wavelength. They give you the wavelength here, and then they give you the time between crests, which is 0.5 seconds, or half a second. The time between crests, the time that it takes to get through that whole wavelength, is the period, but we need frequency. So the first thing you're going to need to do to solve this problem is solve for frequency, which is 1 over the period. And then once you get frequency, you'll multiply the frequency times this wavelength of 10 meters. So our solution, when you take frequency equals 1 over the period, that's 1 over 0.5 seconds. Your frequency is 2 hertz. So your wave speed is going to be 2 hertz, frequency, times 10 meters, the wavelength, which is 20 meters per second. Two common types of waves are transverse waves and longitudinal waves, and these differ in the direction at which the medium vibrates compared with the direction of travel. So if you were to think of holding a slinky on a wall and moving your hand in this first picture here in toward the wall and away from the wall and pulling your hand back and forth, that wave would be called a longitudinal wave. So it's moving, the wave is moving the same direction as, the vibration is moving the same direction as the wave is moving, both towards and away from the wall. A transverse wave is this picture below here that looks more like the waves we've been looking at, where you're going up and down, up and down. So if you were to jiggle your hand up and down, you would get this look in your slinky here. The wavelength is really the same no matter what. It's the time either between, in a transverse wave, between the bottom and the bottom, or the trough and the trough, or the crest and the crest. It's the same thing in a longitudinal wave, it just looks a little different. It would be the same point between either where the slinky or the wave is very compressed to very compressed, or where it's the most spread apart, where it's most spread apart. So again, those are your two types of waves, longitudinal waves and transverse waves. In a transverse waves, again, the medium vibrates perpendicularly to the direction of energy transfer. So again, if your slinky, if you were to move it up and down, your wave would have that sine curve-like look. It's a side-to-side movement. So for example, vibrations and stretched strings of a musical instrument would vibrate up and down like that. Radio waves, light waves, and S waves that travel in the ground, providing geological information, all have that transverse wave movement. Let's do a review question. The distance between adjacent peaks in the direction of travel for a transverse wave is the frequency, the period, the wavelength, or the amplitude. The answer is the wavelength. The wavelength of a transverse wave is also called the distance between adjacent troughs, or between any adjacent identical parts of the waveform. Another question, the vibrations along a transverse wave move in a direction along the wave, perpendicular to the wave, both or neither. The answer is perpendicular to the wave. So again, those vibrations are moving up and down, while the wave itself is moving forward. Let's look now a little bit more at longitudinal waves. In the longitudinal wave, the medium vibrates parallel to the direction of energy transfer. So again, that's like holding the slinky and pulling it back and forth, pulling it in and out away from the wall. The back and forward movement consists of compression. So that slinky gets compressed together and it gets pulled apart. So the compression area where it's kind of pulled together is, we would say the wave is compressed. Rarefactions are just the stretched region between the compressions. And examples of longitudinal waves are sound waves in a solid, liquid, or gas. So examples, sound waves in a solid, liquid, or gas, it has this look below. So again, these areas where the particles, say you're looking at sound moving through the air, when the air molecules get compressed together, that's called the compression. And then rarefactions are the areas where, like your slinky getting pulled apart, those air molecules get pulled apart. And so they are not as densely packed in here, and that's called the rarefaction. P waves that travel in the ground that provide us geological information, they're moving through a solid, and they would have this longitudinal wave, these longitudinal wave characteristics here. Question: the wavelength of a longitudinal wave is the distance between successive compressions, successive rarefactions, both A and B, or none of the above. The answer is both A and B. So just like your wavelength in a transverse wave, you could measure between successive troughs or successive crests, any identical points. Same thing in a longitudinal wave. You're measuring between any identical points in the wave. Now, wave interference occurs when two or more waves interact with each other because they occur in the same place at the same time. So let's say you were to drop a stone in a water and you'd see ripples going through the water, and then you were to drop another stone someplace else and those ripples would meet up at some point. Where those ripples or those waves meet up, we call that wave interference. And the superposition principle says that the displacement due to the interference of waves is determined by adding the disturbances produced by each wave. So essentially, if your waves are moving and they're overlapping in the same direction, the wave is, if you have two waves moving in the same direction that overlap, the wave is going to get bigger. So simple adding, if the waves are going in opposite directions overlapping, then the wave is going to get smaller. So you're subtracting those waves. And whether you're adding or subtracting your waves, like I said, whether the waves are occurring in the same direction or in opposite directions, we call this constructive interference or destructive interference. So constructive interference, this picture here, is if you had two waves that were moving in the same direction at the same time, so the same place and the same time, and what you would end up with is a wave with twice as big of an amplitude. And remember, amplitude is this distance from the midpoint to the crest. On the other hand, if your waves were moving in opposite directions, so one's going up at this point and the other one's going down at this point, the waves would cancel each other out. So you're subtracting your two amplitudes, and you would end up with actually no wave. Next, we're going to look at standing waves, and a standing wave is essentially when the wave is not moving forward or backward in direction, but staying in one place. So for example, if you were to tie a rope to a wall and shake the free end up and down, you produce a train of waves in the rope. If the wall is too rigid to shake, so assuming that your wall doesn't move, the waves would be reflected back, so you would hit the wall and then the waves would be reflected back, and we call that creating the waves and the waves being reflected back form what's called a standing wave. So looking at it on the right hand side, you create the wave going into the wall, the wave gets reflected back against the wall, and if you time your motion just right, you can have the wave be reflected back along the same curve, and you kind of get a nice smooth motion in your rope. If your wave was to be reflected back at the opposite point here, and you were to time it just right or just wrong there, it would cancel the wave out. So again, your waves here are out of phase, and so those the waves actually can cancel each other out. Nodes are the regions of minimal or zero displacement with minimal or zero energy. So as you're shaking that wave back, that rope back and forth, the node is actually, there's going to be a place in that rope where the rope does not move up and down. So your wave is making this motion here as it's going back and forth. And the node occurs where there's zero motion. Now, if your wave was to do this motion here, where the wave going in, or the incident wave and the reflected wave, cancel each other out, you actually have a node all the way along. So you're going to have no movement in your rope all the way along. Antinodes are the regions of maximum displacement and maximum energy. So antinodes would be your point, essentially your crest or your trough. So the points where you're the furthest away from a node. And antinodes and nodes occur equally apart from each other. So just essentially you're looking at a wavelength. So you're looking at the node or the midline to going through to another node, which we can't quite see here. That would be like the wavelength there. And so going from node to node or antinode to antinode, you're traveling the same distance or the same wavelength. If you were to tie a tube to a firm support and shake the tube from side to side with your hand, if you were to shake it with the right frequency, you could set up a standing wave. If you shake the tube with twice the frequency, a standing wave of half the wavelength having 2 loops would result. So twice the frequency would mean that you have half the wavelength and you're going to get 2 loops. If you were to shake the tube with 3 times the frequency, you'd have a standing wave of 1/3 the wavelength, having 3 loops. Some examples of a standing wave are waves in a guitar string or sound waves in a trumpet. So if you think of that guitar string, it's tied down at either end, and the string is just vibrating up and down as you hit the string with your finger. The string's not actually going anywhere, but it's making that up and down movement going back and forth along the string. So again, that's an example. Those are examples of standing waves. Next, we'll cover the Doppler effect, and the Doppler effect can apply to light and sound. And for light, it's an increase in light frequency when a light source approaches you, and a decrease in light frequency when a light source moves away from you. So as a light is moving towards you, you see the light as occurring that more frequently. So if you had like a flashing light and it was moving towards you, you would see the light flashing more frequently when the source is approaching you, and it would appear to be flashing less frequently as the light source is moving away from you. The star's spin speed can be determined by using this Doppler effect, so looking at how the light frequency changes. So for the Doppler effect of light, there's something called a blue shift and a red shift. And a blue shift is an increase in light frequency toward the blue end of the light spectrum, whereas a red shift is a decrease in light frequency toward the red end of the spectrum. So colors that we see are determined by the frequency of light within a certain range. And so as you move up in frequency, the colors begin to appear more blue, and as you move down in frequency, the colors appear to shift toward the red end of the color spectrum. So an example is a rapidly spinning star shows a red shift on the side facing away from us and a blue shift on the side facing us. Review question. The Doppler effect, does it occur for sound, light, both, or neither? And it occurs for both sound and light. The last thing that we'll cover here are shock waves. And shock wave is, if you've ever heard of a sonic boom from an airplane, essentially when the airplane starts moving faster than the speed of sound, the air pressure in front of the plane can't quite move out of the way fast enough as the air pressure, that wave coming from the back of the plane. So the sound wave at the front is not moving out of the way as faster than the sound in the back, and you'll get essentially what they call a shock wave over those two overlapping waves from the front and the back of the aircraft. And with those two overlapping waves, you'll get a loud claps that's very similar to a thunderclap that you would hear on the ground. So anytime that aircraft moves faster than the speed of sound, you'll get that loud clap and that loud cracking noise, and that follows a path in a cone shape away from the plane, and so you'll get a sort of steady rumbling noise coming out of that plane when it's moving faster than the speed of sound that has nothing to do with the noise of the plane itself. And a shock wave consists of two cones. There's a high pressure cone at the front of the airplane and a low pressure cone at the back of the aircraft. And again, it doesn't matter at all how noisy that aircraft in and of itself was before it went faster than the speed of sound or became supersonic. It just matters that once it goes faster than the speed of sound, your overlapping sound waves make that loud clapping noise. Another example of this would be like a supersonic bullet could make that same noise, or the crack of a circus whip could make that same noise.
That's the end of our week 1 lecture. I hope your first week goes smoothly for you for all your courses, and let me know if you have any questions as you go about your work for the week.